So some important links, will be thrown into the chat there. One of them is the LANDFIRE technical documentation, which should help out with a lot of questions that people have. You can download that and look through all the different processes for LANDFIRE. Another one is the landfire.gov site, where all of our a lot of documentation for LANDFIRE is posted. Basically, what LANDFIRE is we distribute data across all lands, not just Forest Service or DOI or just private. It goes across all lands. So we're talking about the continental US, Alaska, Hawaii, Puerto Rico, all the Caribbean islands. Some of the data that we do produce or that we distribute are like existing vegetation type, existing vegetation cover, height, biophysical setting. We'll talk about some of the fuel vegetation layers that we distribute, because we'll be mainly focusing on fuels today, and then a test, I guess, site, or which would be the Cook's Peak fire. And Charlie will show some far site simulations for that. We use a lot of plot data that we collect every year. There's a collection method that's used for LANDFIRE, and then it's all put together in a large database that we distribute called our LANDFIRE reference database. And then we collect plot data and events data. So we collect events data from the FACTS, which is Forest Service, and NIFPORS, which would be DOI or DLM. In general, LANDFIRE is basically an all lands project. So we're trying to give data to all people, all projects that can use vegetation, fire, disturbance. There's really two things I'd like to talk about today that are really related to the Cook's Peak fire, and that simulation is the surface fuel, which is this section here. And what you really need to know about the surface fuels is that they were all derived from expert opinion. We traveled the United States showing fuel specialists how we modeled their surface fuels in the Anderson 13 and the Scott and Bergen 40 fire behavior fuel models. And we got their feedback in terms of, we asked questions like, if you have a certain vegetation type and you have a certain amount of cover and height, whether it be tree, shrub, herb, how would that burn? What would be the rate of spread? What would be the flame length that you'd expect to see? And then you'd equate that to a fuel model. So one of the things that people tend to get confused about is the Scott and Bergen models that we used, even the 13, we're talking about rate of spread and flame length. Now, if you look at them on the surface or look through the GTR, it gives you fuel loading models, right? Or fuel loadings for those models. What are the ones, tens, hundreds, 1,000-hour fuels for those in terms of tons per acre? We didn't actually model them in terms of the fuel loading on the ground. Like I said, we got feedback in terms of rate of spread and flame length. That was most useful for people to assign a fuel model. And then it also works better with the simulation models because they're looking at those things as well. So you want your simulation to be able to model more closely to what the fires did in terms of those rates of spreads, in terms of flame lengths, things like that. Secondly, canopy fuel was modeled more on the plot data for the vegetation from like a lot of it's FIA, but we get plot data from other like universities and other collection methods from different agencies, right? So we use that data, ran it through the forest vegetation simulator to get canopy cover and canopy height equations, so that, and as well as canopy base height, so that you can take a starting piece of vegetation and transition it out to, 5 years later or 10 years later, depending on how long it's been since a disturbance has occurred. Those equations are an important part in assigning the canopy cover, canopy height, canopy base height. And then with bulk density, that comes from a general linear model, which was developed back when LANDFIRE first started. And that uses also vegetation, a starting vegetation, cover, and height to get at what the estimated bulk density would be. So keep those two pieces in mind as we go through this, and I will walk you into how those work. As far as fuel disturbance goes, on the fuel side of things, we take all of our annual disturbances, which is another product that LANDFIRE produces is on an annual basis, is all the disturbance that goes into LANDFIRE. So you can collect those or get those from the LANDFIRE web viewer, I guess we call it now, not data distribution. It used to be called data distribution. In fuel disturbance, there are 7 types of disturbances that we basically aggregated them into. So you got fire, mechanical add. Mechanical add's more like, say, a lop and scatter type of method in silviculture. Or if you did a light thinning and you left the fuel on the ground, that would be a mechanical add to the fuel on the ground. Mechanical removes, like a timber harvest. Weather would be like blowdown. Obviously, insect and disease is another important one. So like beetle kill. Mechanical unknown is an interesting one because it's where we've detected a disturbance in using imagery. Don't have, say, an actual event that was given to us from, say, FACTS, NIFPORS, or even other agencies or state or private. Sometimes they'll give us event type polygons that we can associate with our image detected part. Well, mechanical unknown is just image detected. We don't have a polygon associated with it. So a lot of times those tend to be private areas, not all, but they also tend to be a mechanical remove, like a harvest or something to that effect. Mastication, that's like, you know, using a mastication head to chew up all the fuels and rearrange them and put them compactly on the ground, you know, kind of like chipping or something to that effect. The next one is we have 3 severity classes, low, moderate, and high. What that means is a low is 0 to 25% reduction of above ground cover. So of shrubs or trees or herbs, right? Moderate is 25 to 75% reduction in cover. And then high is 75 to 100% reduction. And then we have 4 times since disturbance periods. So non-disturbed, meaning that there hasn't been a disturbance on that pixel for at least 10 years. There's a time since disturbance 1, which is the first year post disturbance. Time since disturbance 2 is 2 to 5 years post disturbance, and time since disturbance 3 is 5 to 10 year post disturbance. This is a flow chart of how the fuel vegetation is made. Now there's a difference between what existing vegetation type and fuel vegetation type. Okay, so existing vegetation type is what we produce with each update. And you receive that in continuous cover, continuous height, and then the ecological system existing vegetation cover types. Now, the difference between that and fuel vegetation is in fuel vegetation, the ecological systems are grouped a little bit more. Sometimes they're grouped by the life forms so that you can have herb, shrub, tree all in one ecological system. Sometimes in the existing vegetation types, those are separated out, right? In the fuel side, we want them all together because that's how we started building our fuel rule sets way back when in National LANDFIRE. Also, with fuel vegetation type, it is pre-disturbance vegetation. So if you had a disturbance in 2016, we put in vegetation back into it just prior to that disturbance occurring. And we do that by using the previous years of vegetation updates in LANDFIRE. So if we start out in this flow chart, we have our existing vegetation cover, EVC, existing vegetation height, EVH, and existing vegetation type, EVT. Okay. For non-disturbed areas, they all get binned. And I just realized my mouse is not showing things. Okay, they all get binned. So EVC gets binned into 10% bin covers. So 15 to 25, 25 to 35, so on and so forth, up to 95%. And that's for herb, shrub, and tree, but only for a single pixel. It can only be a herb, shrub, or tree for a single pixel. So it starts with a tree. If you don't have at least tree cover of 10%, then it goes down to shrub cover. And if you don't have at least shrub cover of 10%, then it's herb cover. And then if you don't have at least 10% herb cover, it could be barren, sparse, water, something like that. Okay. Same thing happens with the heights. But in fuel world, we try to bin these things so that we have fewer combinations, so that when we make our rules, which I'll show you later, we have fewer rules to make for the different fuel models and covers or canopy fuel. We got to this part, cover and heights binned, the non-disturbed areas are here. That gets put into the fuel vegetation cover, fuel vegetation height, and fuel vegetation type. Now for this next section over here on the left, these are all the previous years, and there's even a few more now that aren't in this flow chart, of updated, of LANDFIRE vegetation updates. And then we add this other piece called the HDIST, which is History of Disturbance. We combine those together in this next piece here. And this will be combined, they're all combined together so that we can develop a pre-disturbance vegetation layer. All that gets combined with the non-disturbed, meaning we take the pieces from the non-disturbed that are improvements, such as water, road, we combine all those together, and then we add them to that last piece. So now we've got non-disturbed and disturbed, or pre-disturbance in fuel vegetation cover, fuel vegetation height, fuel vegetation type. So the reason for going to pre-disturbance vegetation is it gives us as fuel people some place to start, right? And then from that starting point, we can say, okay, if you have a certain vegetation and you have a cover and a height, and then you say that your fuel model, say a timber understory 5, right? Now we can ask the question, if you have a certain disturbance, how does that fuel model change? But you always have to have that starting point. You got to know how much fuel is going into this whole process. So this is how we make the surface and canopy fuel. We start with these pieces over here. We have biophysical setting, fuel vegetation cover, fuel vegetation height, fuel vegetation type, and the fuel disturbance. That all gets put into the LANDFIRE total field change tool. All of that gets combined together, and from there we can make our grids. And once we do make our grids, QA QC them, if we find errors, we send them all the way back to the beginning. Or if we find things that we want to investigate, we send them back to the beginning. Then we run them back into LFTFC, look at the fire behavior. And when we're finally satisfied with what we want, then we get this far right column of canopy fuel and surface fuel model products. Okay. And for the canopy fuel, you've got canopy cover, canopy height, canopy base height, canopy bulk density. For the surface fuel products, we have the Scott&Bergen 13, Anderson 13, Scott&Bergen 40, the Canadian Fire Danger Rating System fuel types. We also produce fuel characterization classification system, fuel beds. That leads me into this next slide. This is the LANDFIRE. This is a window from the LANDFIRE total fuel change tool. This is how we make our rules for how the vegetation turns into a surface fuel model. So if we look at this first piece, this is the existing vegetation or the fuel vegetation type. So if we have a 2027 Mediterranean, California, dry music, mixed conifer and woodland type, we can say, all right, specialists, this is what we did. We have this range of cover, right, from 10 to 100% trees. And we have this range of height from 1.8 meters to 8.9 meters. We can get this fuel model, a fuel model 5 from the 13 and a shrub 2 model from the fuel model 40, the Scott&Bergen 40. And we can adjust those. So you can adjust those ranges, and then what comes out at the end is the number of acres that are affected within that particular management area. Now, For LANDFIRE, the fuel side of things, we look at our units in terms of zones. And you can see, I don't have a picture of all the different LANDFIRE zones, but you can find those also on the map viewer. But these are the different types of rules that we developed with the different specialists. And then this is the fuel model that's associated with them, and then the number of acres for this particular fuel vegetation type. Now, we did these calibrations many years ago, back when we first started with LANDFIRE, but there have been other calibrations that have occurred through, say, Pyrologics. They go through and do a whole bunch of calibrations, and we use that information. They give that to us to use and put into our fuel model rule sets as well. There are other groups starting to do calibrations. We haven't received any data from those, but we'd be more than happy to take that data and look it over if it is available. There's another product that we have in fuel that's called Mod-FIS, which is modeling dynamic fuels with an index system. There's two of them. There's one in the Southeast, which is the index system is the KBDI, which is the Keach Biome Drought Index. The nice thing about this system is LANDFIRE's done a really good job with something new that we're doing with this, and which is a daily update. And I believe that starts in January. Some of the people that are in the LANDFIRE world that are in the chat, you can throw something in there and tell me about, you know, it's not actually January, it's some other time or whatever. But if I remember right, I think it comes back online in January. And you can go into the map viewer and download your adjusted fuels by the drought index for that Southeast area on a daily basis if you want. They may not change daily, but if they do, then the fuel models will change. And there's 3 sets of fuels that it can change to as the drought becomes more severe. One that you'd probably be interested or more interested in with the Southeast side or Southwest side of things is this, our other Mod-FIS product, which is modulated by the NDVI. And what we do is we take the NDVI, we produce an adjusted amount of herbaceous cover and in an increase or a decrease, so that you can get an idea of how things are progressing through the growing season. And we do this, we produce 4 of these products. I'll show you in the next slides when those are produced. And it has been proven to be really helpful to adjust the fuel models up or down, all the way from barren to sparse, all the way up to more volatile covers where we can add additional surface fuel models, such as from a GR1, if you're familiar with the Scott and Bergen 40, you could be adjusted all the way up to a GR3, okay? But there's 4 different progressions. I think it's from non-burn to GR1, GS1, GR2 to GR3. And this is just another slide kind of showing where we model these 4 times a year through the growing season to help those that are doing fire modeling get an adjusted fuel model for this location. Early spring, summer, and fall is when we produce those. And on the next slide, you can see how the area that we produce is kind of in orange here and how that adjusts throughout the growing season. So we want to try to get a product out as early as possible so that people have something to model with. So you can see we start collecting the NDVI in February 1st, and then we stop in April 20th so that we can get a product out roughly by May, the first week of May. The second one, you can see that we increase the modeling area further north for the spring. And this is out roughly the first week of June. And then by summer, we've gone further into our modeling into the north, and that comes out first week of July. And then we do a 4th modeling back in the Southwest again, or just kind of that lower Southwest location again, and that is first week of October. That would make sense. So those 4 products come out every year. I can't remember the exact date when we first started doing that, but definitely look into those. They can be some very helpful things. One of the things we get asked a lot about is if you've been using the fuels data, is we went to this term that was called capable fuels. We started that on our first update, which was remap 16, came out in 2019, I believe. People said, okay, what's capable fuels? This is confusing to me. Well, basically, it's fuels that have been adjusted for the effective year of the analysis. So let's go into that, and hopefully I can explain what that means. So if we look at when the last 4 productions have been or 3 productions for LANDFIRE, I put them on a timeline here. They are named by when the last disturbance was included in the fire history. So if the last disturbance included was 2016, we call that 2016 update, right? So it includes 2007 disturbances through 2016, and it's called version 200, right? The next one, which is the 2011 through 2020, the last disturbance that was included in it was 2020. So we call it LANDFIRE 2020 version 220. And then the same thing with 2013 through 2022, which is the last one we just produced. It's all out and available right now, and it includes disturbances up through 2022. So now let's look at another timeline here. This is a timeline of when they were actually produced. So 2016 wasn't actually produced on 2016. It was produced in 2019. So what that means is initially when we were doing fuels for LANDFIRE, national all the way up through 2014 updates, we coded the disturbances so that if, say, you had a 2016 update, you had disturbances up through 2016, disturbances in 2016, the time since that disturbance would be a 1, meaning it was within 0 to 1 years, right? If it was 1 to 4 years before that, it was in that time since disturbance 2, 0 to or 1 to 4 years. The problem lies that and it wasn't really a problem. People knew what they were getting, because that's when the year was, or the update year. But we thought, okay, how could this be more helpful for people? How could they use this more in their disturbances? Well, if you have a 2016 disturbance, it's not all that helpful to call it the previous year when you're in 2019, right? Fuels have changed over that 4 years to where it's not immediately right after the fire, it's actually in 2019. So you can see that there's that difference in years there. So what we did, and this is just to remind me to tell you the issue is, there's been time since that disturbance. It's not, if you code the disturbances according to 2016, then you're already 4 years behind, right? So what we did was we made capable fuel. So now I've got this third timeline down here, and it says capable fuels 2019. Well, what is that? Okay, well, you take the effective year of the fuels data, which is 2019. Say this would be the year that you were going to actually be using it. We produced it that year. You're going to use it that year. You want the disturbances in the, or the fuel in the disturbances to reflect that you're going to be using them in 2019, not 2016. So what we do is we adjust the time since disturbance. We age them out, right? We update the time since disturbance using the current year up here, 2019. And then we reassign the fuels to those disturbed areas. So we know that a 2016 fire in 2019 is going to react differently than if it was a 2016 fire in 2016, right? So that's really what capable fuels is. It's the fuels are adjusted based on the time since the disturbance of all those disturbances we have recorded. So we've done that a second time since remap, and then we produced that for the 2022 fire season. So we have capable fuels, or 2020 fire season, sorry. So we have a capable fuels 20. And then we went into another update. Then we had update LANDFIRE 2020, version 220. Now we have what we call capable fuels 2022 out here, because the last disturbance that went in was 2020. We adjust the time since the disturbance. So we know a 2020 disturbance would be already 2-3 years old. So we adjust the fuel based on that. Now we call it 2022 capable. So it's usable for 20. We don't actually add any more disturbances in. It's just capable for use in 22, right? We're still using the same disturbances. We're just adjusting the time since the disturbance and then reassigning the fuel. So now we're only a few years behind here. So if we go to our next piece in 2023, which is where we're in now, we just finished 2022. The exciting part is we're only a year back, which is perfect. It's where you want to be. You want to have all your disturbances in place for the year you're going to be using, which is 2023. We have all last year's disturbances from 2022 in. So now we come straight down to the capable fuel line, and it doesn't say capable anymore. What does it say? It says fuels 2022. We don't need capable here, right? So now we're changing the naming of it. So now it doesn't say capable fuels. When you go on the viewer, it's going to be fuels 2022 because we don't need to do capable, right? So then the following year, we're going to start into our update 2023. It's only 1 year behind. We'll be producing it in 2024, which is perfect. We're getting disturbances all the way up through 2023. And now when you go down to capable, it's going to be called fuels 2023. So how are you going to find those? So let's go to our LANDFIRE map viewer. We'll start with our 2016 stuff, and which you're probably familiar with. You go under 2016 remap, and it says, okay, fuels 2019 capable. We saw that on the previous slide. You could get all your capable fuel there. Then we went to a 2020 capable and get that there. Then when we had update 2020, which is version 220, you go under fuel capable or fuel 2022 capable, you get your fuel there. Well, now the next piece is we have a new update that just came out, and it's 2022. So with 2022 version 230, now you go into there and it doesn't say capable of any year. It just, because you already know it's part of LANDFIRE 2022, it's year 2023, you just grab your fuel there. So now when we go do an update for 2023, it's just going to have fuel in there. It won't have a capable tag on it. There's another piece to this, which is the LANDFIRE product services. Okay. And you can see here, when we were doing capable fuel, it had the different years next to, like, say, the fire behavior, Scott and Bergen 40, it would say 2019, 2020, 2022. Now it's going to be back up in this piece here. It's going to be version 230, fire behavior fuel model 40, and it's just going to be right under Scott and Bergen fire behavior fuel models. And here's the website URL for it. So you can get to here, get data. You can find the LANDFIRE map viewer there, and you can also find product services there, which is a different way of getting there. I'm not going to go into it now, but it tells you how to use it if you want to go that route, which is really handy. I highly recommend using it.
You're going to hear me talk about several different layers throughout the course of my talk. And don't fret about it. I put them in this PowerPoint that I can leave for you on where you can find them and a little description of what they are. But they're all valuable assets when it comes to modeling a fire behavior, especially if you're assessing fuels like we're doing here for LANDFIRE. We do these evaluations occasionally. Our site, maybe every other year or so, but with every geo area, we do a fire behavior analysis to make sure the data looks fairly consistent with what we've had in there in the past. That being said, let's get right into the modeling of it. Let's get you into focus on where we're going to talk about. We're in northern New Mexico, as you can see here. All right, so here we are in northern New Mexico. Santa Fe is just to the south and west a little bit. To the north is Cimarron and the Boy Scout Ranch at Philmont. And then there's not much else up there until you get up into Colorado. So it's kind of wide open territory, large ranches, that sort of thing. This particular screenshot has the fuel models that we're going to be looking at within the fire area. Now, let me go ahead and first back up and see if I can get ArcMap to show for you. Are you seeing ArcMap?
Yes.
All right. So this is the complete fire area of the Cooks Peak fire. What we were looking at before is this little section of it down here. This happens to be Cook Peak right here. What I want to show you in this slide is the vegetation type that permeates throughout the interior of this fire. This whole blue area is one specific vegetation type, which is Southern Rocky Mountain ponderosa pine woodland. The fuel models run something like this. Well, they run exactly like this, only in the non-disturbed areas, which most of this was. There was a few older fires within this fire perimeter that'll show up as non-burn later. But the fuel models are generally GS2 for the short trees and the moderately open trees, GR2, which is a grass 2, for the very open trees, 10 to 19%. And then heavy timber TU5 takes up most of the moderate range of cover. So from 30% to 49% tree cover, you have a timber understory 5, which is notorious for being able to torch. It puts out enough heat energy from the surface fuel model to get the canopy involved. And in this case, we'll see that it's involved in mainly torching instead of active crowning. Once you get above 50% tree cover, it calms down to a TL8. It's mostly litter on the ground. There's a lot less large wooded debris on the ground. It's more open, and it burns more like a timber litter model, according to the people that did the calibrations for this area. So that's the non-disturbed state of that blue area that you're looking at right here. Now, what we're going to do is we're going to take the fire and we're going to take a look at the first 5 days of spread to see how the LANDFIRE data does, it's compared to what the fire boundary is. We are going to utilize several different layers to help us get an honest evaluation. When you just download the landscape file, which goes into FarSight, it's not going to have some of these roads in it. Most of the roads that are in the landscape file are major roads like I-25, which is just off to the east here. And some of these roads might be in there, but most of them probably not. So on that LANDFIRE site that Tobin just showed you, if you go to the Fuels tab and you go about halfway down the page, you'll see an operational roads layer. It's very handy. It's very important that if you're going to do some kind of a fire analysis, a fire spread analysis, that you have all the structures that might be in the way that would impede fire spread and fire behavior. So when we just downloaded the landscape file, this road was not in there, and we couldn't figure out why we were getting a lot more spread than this particular perimeter, which is the first 2 days of spread on the fire. And then once we put in the roads layer, we can see why, because it gets hung up on this road and it has to do some spotting to get across. We also got another layer, which is also in that PowerPoint for you, from the specific incident data FTP site out in NIFC. And there's a link to that in that PowerPoint. But it's very important. You can download all the information that they took when they did this fire, all the IR screenshots. This one is an IR, but all the other perimeters that we'll look at will be infrared that they fly in the evenings to see where the fire is and where the heat is. You can get the isolated heat layers, you can get the scattered heat layers and the intense heat layers, along with the perimeter. You can go to the GIS portion of what's on that FTP site, and they'll show you where they've been trying to do some suppression activities, which is also very important because it impedes fire spread. And to do an honest analysis of the fuels, you need to know where all those impediments are. As you can see in this particular portion, it was early on in the events data of the incident, and they only had these two little tractor lines out here, and they weren't connected. And so when we would do our runs, once we got the roads in there, we got everything in there, when we'd do our runs, it would come right through this little hole, which is not in the final perimeter. So when you look at a couple of days later in the events data, you'll see that they close this gap. They hold the fire at this particular point along, or this particular line, running north and south here. And we'll take a look at that as we watch the simulated fire grow. So as I was saying, this perimeter depicts, well, the Cook Peak fire started in April of 2022 on the 17th. It was reported to dispatch after 4 o'clock, just after 4 o'clock on the 17th. We started our analysis at 3 o'clock in the afternoon to allow for some fire growth before it was spotted and reported. So our first perimeter, when we do the analysis, well, we took into account a burn period from 3 o'clock in the afternoon until the humidity started coming up to a point where we cut off the burn period. So this is what we ended up with as far as spread for the 17th. Now this perimeter data that you're looking at here is for the 17th and the 18th. And it's hand drawn, it's not IR. So people that were out on the fire, they were saying this is where the fire's at. This little neck that runs to the north is a little bit hard to understand, and I'm not sure exactly, how accurate that is. But anyway, that's the perimeter that we're shooting for, and that we'll shoot for in the very next day as well. Mostly this fire and this vegetation type that permeates throughout the fire is fuel model TL8, which is this bluish green color. If it's bluish green, that's the way I see it. And the darker color is TU5. As you come up to the mesa tops, this brown color is the GS2 that's involved in that vegetation type, and the orange colors is the GR2. There's several different vegetation types that contribute to that GR2, not just the ponderosa pine one that we looked at the rule set for, but also there's some subalpine meadow vegetation types up here as well that contribute to that GR2. The GR2 is the greener color, I do believe. I could check the legend. But the ones that you really want to track in this evaluation are the timbered areas that are actually contributing to the fire spread through spotting, because that's what this fire travels with, is with the spotting that's occurring from the torching in the trees. So you can get a complete list of the fuel models that are located in here and all the vegetation types, and I can add them to that PowerPoint if you're interested. So the first day, the 17th, we run out to about, I believe it was 2100 when the humidity started to come up and the temperatures started to go down. And once humidities get to that point where they're, in the mid 20s or so, and the temperatures dropping into the 50s, the fire behavior is really going to settle down. It's April after all. So what we did in order to try and match the 2-day perimeter, we did a second day run. And it brought our simulated fire out fairly close to where their hand-drawn perimeter is. The only really excessive area that overpredicts in this particular run is the southern southern end. And we had trouble with that all the way through, as far as not conforming to what the fire did. But there's several reasons for that, I believe. This line here that they were using for an anchor point, later on in the events tab, you can see where they took a cat line out to this meadow area out here, this meadow complex. And I believe originally they were able to hold the fire along that line until it got established out this way and cooled off in here to where it wasn't going to spot down into here. So mainly the fire just went this way. But anyway, you'll see throughout the 5 days that we project here that this south area is going to continue to burn over into this portion of the landscape. And, you know, it eventually does, but not within the 5-day period that we're looking at. So, you know, all in all, if you're evaluating LANDFIRE data, I would say the points of concern on where this fire is probably going to go, we're hitting pretty close to where we need to be. The front of the fire is out into here, and we're pretty close. I don't like to underestimate, and I don't like to overestimate. I'd rather overestimate just a little bit, especially if I'm doing some kind of evaluation in an operational sense. You want to try and overestimate, but not to the point where you scare everybody to death. You want to overestimate to give operations people time to get their work done and feel fairly safe about it. So we'll take a look at the next 2 days. The very next day that we ran in the simulation, well, let me put up the perimeter for the next 2 days. The next perimeter we get is this one here. They didn't fly IR and nobody drew it on the 19th. This comes in at on 4/20 at about a little bit after midnight. This IR shot comes in. So this is the next perimeter that we're trying to evaluate the field data against in terms of fire spread. Our 19th looks like this in terms of fire spread. Oops, wrong one again. So that's the 1 day, and you can see where this is going to go right through that little hole there. And it eventually does, but what we did for this analysis is we saw that they held the fire here, and so we buffered this. We didn't buffer it. We barriered this to a point where it couldn't escape through this little hole. And in our final projection, it'll follow pretty close to the barrier, which is the actual place where the fire where they held the fire. To come up to this particular perimeter, we'll take a look at our 4th day spread. So we're pretty close up here in terms of where the fire is really heading. It's starting to go in a more northerly direction. So the winds are generally shifting to a southwest direction from the northwest and the north that they had been blowing. For the weather evaluation in this assessment, we looked at 5 different remote automated weather stations that are in close proximity to the fire. The link to where you can get data from those raw stations is also in the PowerPoint that I'll leave behind for you. But we ended up using the Truchas station, which is just off to the southeast of the fire here. The closer one was Bartley, but it had really different wind speeds than we thought were going to occur on this fire. Truchas had the wind speeds. It also had the direction that we needed to go with the fire, and it lays in the same range as the origin of this fire. So that's why we ended up using it. We looked at Taos. It's up on the divide, and it was very windy. It would have blown this fire all over in the simulation. So we didn't use it. We looked at one out here in the plains, and it was also very windy and directionally the wrong way as well. So we use Truchas, and like I say, the link to where you can find that weather data is in the PowerPoint. So once you get to a point when you're doing these evaluations where you get 4 and 5 days out on a fire and you're going along fairly well, you know, there's really no sense in doing the rest of the fire if you think you can pretty well match where the perimeters go. The last perimeter that we took a look at would be on the 22nd at 06:30 in the morning. And it's the yellow line that goes up to the north a bit. And again, the south area is going way further than we'd like it to. And we'll take a look at that in a minute. The simulation that we ran to match this particular perimeter, and you can see this road up here is going to be an impediment, and it does get hung up along that road for a certain amount of time. If you come in real close and look at the spread lines, you can see they're bunched up in here, and then spotting occurs and it's able to travel across that road. The same thing happened in this road down here we were looking at earlier. This was our projection against this perimeter here. It over predicts a little bit all the way around, just a very little bit on the top end. Of course, the south end is a long ways away from where we'd like it to be. But I believe, you know, the very first night, we had some northerly winds and we got some spotting activity down there, and it just never gave up after that. Let's take a look at where some of those spot fires are. This is fairly early on, but this is where Farsight projected the spotting to occur. And as you can see, that's where it gets hung up on this first road until it spots across. And then you start getting these waves of frontal fire going. The same thing occurs on this road up here to the north. I'll have to get a different spot fire map from a later date. I guess I don't have one in here in Google. I don't have one late enough to show it getting across this road in Google. We do have that in Flam Map though. Anyway, I think you get the point. The projections that we're seeing here are fairly close, a little bit of over prediction, which is fine. I'd rather be a little bit over than under like this one was. The only one that really concerns me is the south end of the fire. And I think we could adjust the barrier file to hold that fire along out to this metal complex if we wanted to rework, you know, what we were putting in there for barriers. And we could probably hold this spread down a little bit. The final fire size though is gonna come right out to this ridge anyway. So this is all gonna be included in the fire. In the final. But I think overall, the off-the-shelf LANDFIRE data, now I'll say off-the-shelf, but I want to qualify that by saying that we did download, we downloaded the LCP for the early spring Mod-FIS, and that makes a big difference. In the regular off-the-shelf LANDFIRE, all this orange area out here is normally a GR2. In this particular version of the Mod-FIS data, it is lacking in herbaceous cover, and the fuel model ended up being a GS1. And that makes a big difference for when it comes off the mesa tops and out of the foothills down into the plains. You don't want a run of real thick grass burning heading toward you when you're operating a dozer out here. But if you have something that's going to burn like a GS1, it's pretty easy to put tractor line in and hold the fire. So there was some changes there. There wasn't much change to the upper elevation meadow areas. They remained the GR2 in most instances. So in that particular Mod-FIS landscape. But it was very, very handy to have the Mod-FIS for the final extent of the fire. And it was also very important to have that operational roads layer and the incident-specific data to show where the impeded, to show where areas that are going to slow and stop the fire. We can emulate that within the program and not have fire running all over the place when it's been impeded by something. So those would probably be the important points. You want to make sure that you can get all the data, that type of data that you can find before you run your simulation, to make sure you have it on hand. We'll just take a look at the final fire size and SLAM map. The black line here is the final fire perimeter. This is our 5-day spread. You know, if we were to run it out for the length of the fire, there is a rainy period in there. Not a lot of rain, just a little drizzle thing. But I'm sure we would have been fairly close to hitting the end point well enough with Farsight. We would have had to strengthen these barriers over here for once it comes off the mesa to make sure that it wasn't going to run out into the plains very far. But that had been done in the events data. So this final fire line out here held it in here and in here where we snuck out originally, and then reinforced the barrier there. And the final fire size also includes what we over projected for the southern spread of the fire. So in a nutshell, you know, just off the shelf kind of LANDFIRE data can get you in the ballpark. It can definitely give you good information to pass along to the operations people, especially stuff like this southern area that's not burning in their mind because the fire is going this way, but it has great potential to do that. So that should clue you in as to what to make them aware of. The idea that spotting is carrying the fire is pretty obvious once you look at all the spot fires that are occurring from torching. The FLAM map basis tells us that all this orange area in here is torching. Let me turn the spots back off. The yellow areas are surface fire. So we don't see any areas that FLAM map or Farsight projects to be active crowning, but a lot of prolific torching and a lot of prolific spotting. So that's what's carrying the fire through this particular landscape.
From Ryan about how the LANDFIRE disturbance data is connected to snag hazard analysis in the RMA dashboard.
Yeah, well, you know, that's a really good question. Most of the work that's been done on snag deterioration, I don't know. It depends on where you're at and where your snags are located. But if there's snags that were developed or recruited in previous fires, like where I live currently on the west side of the Cascades in Oregon, those snags can be around a long time. If you look at the research and all the models that they have for the snag fall, those should all be down, but they're certainly not. And there's a lot of fires down in my old stomping grounds that you can go out there, and that's the reason that the tactics on more recent fires have been way back away, far away, is because of all the snags that are still standing from the fires that we had in the 80s and 90s. And most modeling will show that those snags would be down by now, but they're not.
Yeah. The snag research that Karen Riley put together, which I think is in the RMA, the LANDFIRE data that was used to produce that was all the LANDFIRE vegetation data. So it was all the plot data was imputed from that, and then Karen Riley developed her snag layer from that. So I guess that's kind of a progression as well from LANDFIRE
yeah,
to.
You know, and I haven't had a chance to really look at that. I did talk to somebody about it on, I can't remember what call it was, but they had a recent fire down on the Willamette, and I suggested that the reason they took the tactics they did was because of the Warner Creek fire and the snags in it. From the Warner Creek fire was 1992, and they went, oh no, the research shows that those snags are all down. Well, I had just been out to that fire, and those snags were not down. So anyway, that's where I'm coming from with it. They did tie this back to how it's used as far as disturbance goes in the future land fire data. I wanted to show you what we came up with, or what has been come up with for the severity of this fire. Red areas are high severity, the yellow areas are moderate severity, and the green areas are light severity. Dark is non-burn. So that makes a big difference, you know, when we're transitioning field models. Since we do have a TSD1, a time sense disturbance 1 now in the data, these high severity areas are going to be pretty non-burnable for that first growing season in our field model transitions. As you get out 3, 4, 5 years, you start to see the shrubs and the grasses come back, and you start to see more burnable field models. And then in these lighter areas where it was a light burn, you may have some fairly significant reduction in burnability the very first growing season after the fire, but it comes back relatively fast and usually ends up being back to the same field models and not that it was before. It was non-disturbed by the time you get to the third time step. Time steps, I think Tobin went over it, but we now have a TSE1. This is the first version of the data that has a time sense disturbance 1 that looks at that first growing season. Then we have a time step 2, which looks at 2 to 5 years after the disturbance, post-disturbance. And so we would usually look at that, you know, that second and a half growing season, halfway through the second growing season, or in some cases, maybe the third growing season, if we knew it was an area that came back slowly. The third time step is from 6 to 10 years out post-disturbance. And so we usually look at something around the 7th growing season or the 8th growing season. Now that changes depending on what geographic area you're looking at. In the Southeast, it returns much faster. In the Southwest, depending on weather, it could take a while to get vegetation growing back to the state that it was prior to the disturbance. So anyway, this is the FDIS from this most recent version of the land fire data, which includes the Cook Peak fire, because it was a 22 fire. So it's involved in our data for this year. So that's a first, being able to look at a disturbance this soon after it happens and have severity assigned to it. And also the time step 1 field model is a new thing for this particular version of the data.